High above the Arctic Circle, in a remote, snow-swept valley in central Norway, the darkness of the long winter night is frequently shattered by something that defies conventional explanation. Brilliant orbs of white, yellow, and red light silently materialize above the tree line. Some hover motionless for hours, anchoring themselves against the biting wind, while others dart across the sky at speeds that outpace modern aircraft. This is not a fleeting, once-in-a-lifetime anomaly. It is a persistent, ongoing spectacle that has transformed a quiet Scandinavian landscape into a living laboratory. We investigate the Hessdalen Lights, a profound scientific puzzle that continues to challenge the very boundaries of atmospheric physics and geology. While sporadic accounts from local farmers date back over a century, the phenomenon demanded global attention during a startling escalation between 1981 and 1984. During this intense window, residents of the Hessdalen Valley reported seeing the mysterious lights up to 20 times a week. The sheer volume of sightings stripped away the easy dismissals of misidentified stars, distant car headlights, or early theories of UFOs. Families watched from their porches as luminous spheres the size of cars drifted over their rooftops, sometimes illuminating the snow with the intensity of a stadium floodlight. The local community, bewildered but desperate for rational answers, catalyzed an unprecedented wave of scientific research. In response to the overwhelming eyewitness testimony, researchers established Project Hessdalen in 1983, dragging heavy optical and radio equipment up the freezing mountain slopes. Capturing a transient, unpredictable event in sub-zero temperatures proved to be an immense logistical nightmare. Batteries drained in minutes, camera shutters froze solid, and the harsh terrain fought the scientists at every turn. Yet, the dedication of these early investigators yielded the first concrete, empirical data. They were no longer relying on human memory. They were recording hard, measurable evidence of an unexplained natural phenomenon. The data captured by those early instruments revealed behaviors that deepened the mystery exponentially. Spectroscopic analysis, which breaks down light into its component colors to identify chemical signatures, indicated that the orbs were not solid objects. Instead, the readings suggested they were composed of a glowing gas or plasma. Even more baffling were the radar returns. On several occasions, the equipment registered strong radar echoes moving at thousands of miles per hour, yet the sky remained completely dark to the naked eye. The phenomenon was operating on frequencies both visible and invisible, slipping in and out of human perceptual range. As the raw data accumulated, physicists began to formulate complex models to explain the luminous spheres. One leading framework is the dusty plasma hypothesis. Scientists hypothesize that microscopic particles of atmospheric dust become highly charged, clumping together to form a plasma state. Unlike the plasma found in stars or neon signs, this dusty plasma can self-organize, creating stable, glowing structures that float through the air. This theory elegantly accounts for the visual ability to hover and change shape, suggesting a complex interplay between ionized gas and the specific atmospheric conditions of the region. But what provides the tremendous energy required to ignite and sustain this plasma? The answer may lie beneath the soil. Geologists mapping the valley discovered a highly unusual topographical and mineral structure. The region is bisected by the Hessdalen River, with iron and zinc deposits dominating one side and copper-rich rocks on the other. Acidic water leaking from local sulfur mines flows between these mineral-heavy banks. Researchers suggest this specific geological architecture essentially forms a massive natural galvanic battery. The entire area might be generating its own electromagnetic field, creating the perfect incubator for atmospheric anomalies. Another compelling geological explanation focuses on the immense tectonic forces at play. The bedrock of the region is packed with quartz, a crystal known for a property called piezoelectricity. When quartz is subjected to extreme physical stress, such as the shifting of tectonic plates or microseismic activity, it generates an electrical charge. Some geophysicists argue that the intense pressure deep within the Norwegian crust forces a massive release of electrical energy to the surface. Upon hitting the atmosphere, this concentrated charge could excite the air molecules, resulting in sudden, brilliant bursts of light. Yet neither the natural battery nor the piezoelectric effect fully accounts for the sheer duration and intensity of the most spectacular sightings. A standard electrical discharge, like a lightning strike, exhausts its energy in a fraction of a second. The luminous spheres have been documented burning steadily for over 2 hours. Calculations based on their luminosity suggest an energy output reaching 2.5 megawatts, concentrated within a sphere only a few meters wide. If these are simply sparks generated by stressed quartz or a geological battery, the mechanism sustaining their prolonged, intense burn remains a glaring void in our current understanding of physics. To bridge this gap, the methodology of observation had to evolve. In 1998, researchers installed an automatic measurement station, affectionately known as the Blue Box. This autonomous observatory was equipped with continuously running optical cameras, magnetometers, and weather sensors, designed to cross-reference visual sightings with precise environmental data. The goal was to remove human error entirely and catch the anomaly in the act, analyzing the exact atmospheric pressure, humidity, and electromagnetic background at the precise millisecond an orb ignited. The continuous surveillance unveiled behaviors that defy simple combustion or electrical models. High-speed photography captured the lights exhibiting a complex internal structure. Rather than a single uniform sphere, some images revealed clusters of smaller, distinct light points orbiting a central axis, almost like a miniature solar system. Furthermore, these clusters were observed splitting apart, moving independently, and then merging back together. This level of structural integrity and fluid dynamics strongly suggests a sophisticated electromagnetic containment field, holding the plasma together against the dissipating forces of the wind. The rigorous, unyielding approach of the scientific community slowly transformed the narrative surrounding the valley. What was once whispered about as folklore or dismissed as wild exaggeration became a respected, albeit frustrating, discipline of study. Universities across Europe began funding student expeditions to the region. The isolated mountain community found themselves hosting international symposiums. The lights were no longer just a local curiosity. They were a recognized scientific frontier, drawing brilliant minds eager to crack a genuinely unexplained puzzle. Despite decades of high-tech surveillance, the core mechanism eludes absolute definition. One of the more recent and heavily scrutinized hypotheses involves the combustion of scandium, a rare earth element found in the local soil. Researchers hypothesize that atmospheric dust, rich in scandium, is ignited by the ambient electromagnetic field. When scandium burns, it produces an intensely bright, white-yellow light, perfectly matching the visual profile of the most common sightings. However, exactly how this dust achieves the critical density required to ignite in mid-air and why it forms perfectly spherical shapes are questions that continue to mock the data. The implications of solving this puzzle stretch far beyond a single Norwegian valley. If the anomaly represents a previously undocumented method of energy storage and release, the technological applications could be revolutionary. Understanding how nature sustains a stable plasmasphere in the open atmosphere could unlock new pathways in fusion energy research or advanced propulsion systems. The phenomenon is not just a quirky trick of the light, it is a demonstration of physics operating at a level we have yet to master, a natural blueprint waiting to be deciphered. As the harsh winter descends once again on central Norway, the automated cameras of the research stations continue their silent vigil. The Hessdalen Lights remain a testament to the enduring mysteries of the natural world, a reminder that our planet still holds secrets capable of baffling our most advanced instruments. Through patient observation, rigorous data collection, and a willingness to entertain radical new theories, the scientific community inches closer to the truth. The investigation stands as a powerful journey of grounded discovery, proving that the most profound scientific breakthroughs often begin with a simple, unexplained light in the dark.